This is the AMC 10B 2022 problems 11 through 15. This is the AMC 10B problem 11. All the high schools in a large school district are involved in a fundraiser selling t-shirts. Which of the choices below is logically equivalent to the statement no school bigger than Euclid HS sold more t-shirts than Euclid HS? Okay, so this is a question about logic statements, right? So what we need to do is we need to go through each of these statements and we have to conclude whether or not the statement is the logical equivalent to the original statement. So let's try doing that. Okay, so let's look at A. All schools smaller than Euclid HS sold fewer t-shirts than Euclid HS. Okay, well, let's also look at E because they have something in common. All schools smaller than Euclid HS sold more t-shirts than Euclid HS. So they're just saying different things, but they're both talking about the schools smaller than Euclid HS. And the reason why this is important is because what this statement is talking about is it's talking about schools bigger than Euclid HS. In particular, what it's saying is basically if you have a school that is bigger than Euclid HS, then they definitely did not sell more t-shirts than Euclid HS. So that is a statement about schools bigger than Euclid HS, not schools smaller than Euclid HS. Thus, statements such as A and E are wrong because they're trying to say something about the school smaller when the original statement didn't even talk about that. Okay, let's look at choice B. No school that sold more t-shirts than Euclid HS is bigger than Euclid HS. Okay, so these two statements are pretty similar, but they're kind of like these two statements, the if and the then, are swapped, and it's also negated. So like both sides are negated. So let me explain. No school bigger than Euclid HS sold more t-shirts than Euclid HS. Well, what that means is that for every school that is bigger than Euclid HS, they did not sell more t-shirts than Euclid HS, right? So basically, we can try to think about how, like, whether or not these two statements are equivalent by thinking about what cases would falsify them. In other words, if I could come up with a school that broke what this statement was saying, right? If it disproved the statement, what school could I come up with? Like, for example, the only way that a school could disprove this statement is if we had a school that was both bigger than Euclid HS and it sold more t-shirts than Euclid HS, because that would violate the fact that no school bigger than Euclid HS sold more t-shirts, right? And if we look at B, what would violate this statement? Well, it's actually the same thing. It's just a school that both sold more t-shirts than Euclid HS and is bigger than Euclid HS, right? And those are just two statements that are requirements. And whether or not like it's this one and this one, or it's the second one and then the first one, or the first one and the second one, right? It's still both of those statements need to be true in order to falsify the statement. So basically, these two statements are actually equivalent because they are negating the exact same scenario. Even though they might not seem like it, B is actually the correct answer. However, there is still more we have to go over, specifically C and D, especially C, because C is very tricky. So first, let's look at D. All schools that sold fewer t-shirts than Euclid HS are smaller than Euclid HS. Well, once again, this statement is talking about schools bigger than Euclid HS and how none of them sold more t-shirts than Euclid HS. Right? This statement is saying all schools that sold fewer t-shirts than Euclid HS are smaller than Euclid HS, which is actually the wrong way around, right? And it's also referencing schools that sold fewer t-shirts. So if we can try to think about what kind of school would violate this statement, it would be a school that sells fewer t-shirts and is bigger than Euclid HS, right? However, that kind of a school would not violate this statement, right? Because a school that's bigger than Euclid HS but sells fewer shirts doesn't violate the statement. So basically, this is talking about the wrong type of school. So D is incorrect. And finally, we get to C, which is actually, this is a very misleading problem because C could be thought of as the correct answer. all schools bigger than Euclid HS sold fewer t-shirts than Euclid HS. So this is the exact same statement as the original, right? Basically what this statement was saying is that all schools bigger than Euclid HS did not sell more t-shirts than Euclid HS. So the only difference is they did not sell more t-shirts or they sold fewer t-shirts. But there is a very, very key thing that is being left out, and that is the fact that schools can sell the same number of t-shirts as each other, right? For example, we could have like school X and they sell 27 t-shirts and is bigger than Euclid HS. And we could have Euclid HS, who is the smaller school, but they also sold 27 t-shirts. And that would not actually violate this statement, but it would violate this statement because it's not fewer. So actually, in that specific scenario, C disagrees with the original statement, and therefore it is not equivalent. So we have arrived at our answer of B. Okay, this is AMC 10B problem 12. A pair of fair six-sided dice is rolled n times. What is the least value of n such that the probability that the sum of the numbers face up on a roll equals 7 is at least once is greater than 1/2? So this is a classic example of complementary counting, right? So it's going to be very hard to count the probability that over n times the sum of the numbers like summing up to be 7 being 7 at least once is very difficult, but it is very easy to figure out the opposite, which is the probability that it never happens, right? So let's think about it. What is the odds that on a single six-sided dice or two six-sided dice, the sum of the numbers is 7? Well, there's 36 possible scenarios, right? 6 times 6. And there is 6 possible possibilities for the sum to be 7. Right? 4, 3, 5, 2, 6, 1. These are our 6 possibilities. And therefore, the probability is 6 out of 36, which is 1 out of 6. So the probability of it not occurring is 1 minus 1 over 6, which is 5 over 6. And the probability of it not happening n times is 5 over 6 to the power of n, because each time we roll it, they're independent events. We're just multiplying 5 over 6 by itself over and over. And the odds that it happens at least once is just 1 minus this probability. And we want this to be greater than 1/2. And there we go. That's the inequality we need. So to solve this, we move the 1/2 to the left side, and we move the 5, 6 to the n to the right side. And I'm just going to distribute that and write that. And finally, if we cross multiply, we get this. So the question is, what is the least value of n that makes this inequality true? So we can try n equals 3. Right, we can try n equals 1 and n equals 2, and we'll see it doesn't work. And I'm just showing n equals 3 because it's the last one where it doesn't work, which gives 250 and 216, which is not true. But then n equals 4 works because we have, if we plug in n equals 4, we will get 625 times 2 basically, which is 1250, and 6 to the 4, which is 1296. And 1250 is less than 1296, right? So therefore, the minimum value that makes the probability greater than 1/2 is just n equals 4. Okay. This is problem 13 of the AMC 10B. The positive difference between a pair of primes is equal to 2, and the positive difference between the cubes of the two primes is equal to 31,106. What is the sum of the digits of the least prime that is greater than those two primes? Okay. So we have two primes. Let's call them P and Q, right? So the positive difference between them is 2. So let's just say P is the greater prime. Then P minus Q is equal to 2. And the positive difference between the cubes is equal to 31,106, which is a pretty large number. Okay. What is the sum of the digits of the least prime that is greater than those two primes? That's just one we solve for the 2. And the thing is, we don't even need to worry about the fact that they're primes. That's the main gist of this. We don't need to worry about it. We just need to solve for P and Q, because we have a system of 2 equations and 2 variables. So let's just do this. P equals Q plus 2. And now we plug in here. Q plus 2 cubed minus Q cubed is equal to 31,106. And cubics are very difficult to solve, but if you'll notice, the 2 cubic terms we get on this side cancel each other out. So we get Q cubed plus, and then 6Q squared plus 12Q plus 8 minus Q cubed is equal to 31,106. So actually this cancels out and we just get 6Q squared plus 12Q. And then if we subtract this, we get minus 31,098. And that is equal to 0. And now we can divide everything by 6. So 31,098 divided by 6 is 5,183. Yeah, there we go. All right. So now we have to solve this quadratic. And in order to solve this quadratic, we basically, the thing is, this is a very large number, and we could try to look for integers Q that work, or we could just use the quadratic formula. So -2 plus or minus, but the thing is Q has to be positive, so it has to be plus the square root of 4 plus 4 times 5,183 over 2. So now if we distribute that over 2, we get 1 plus 5,183, which is just 5,184. And now if you think, what is the square root of 5,184? So we know that this, it's 4. We can try different numbers. I think because this is near 4,900, which is 70 squared, we can try 72 squared. And if we try 72 squared, we get 4,900 plus 280 plus 4. And sure enough, that's exactly what 5,184 is. So we know that it's 72. So we just get -1 plus 72 is 71. And that's our value of Q. So our value of Q, that's 71. Our value of P, that's 73. Those are both primes. So basically that's a way of checking our work. We know that we got the right numbers. And the sum of the digits of the least prime that is greater than them, well, the next prime up from those two is 79. And the sum of the digits is 16. Okay, this is problem 14 of the AMC 10B. Suppose that S is a subset of 1, 2, 3 through 25, such that the sum of any two elements of S is never an element of S. What is the maximum number of elements S may contain? So yeah. All right. So we should try experimenting to figure out what's the highest value we can try to obtain. And then we should try to prove to ourselves that that is the highest number we can obtain. Okay, so let's try to show that. So let's just try starting with the number 1, right? If we start with the number 1, then the number 2 is out, because if we put number 2 in, then we'd get 1 plus 1 equals 2, which is not allowed, because by the rules, it's not necessarily distinct, just the sum of any 2 gives another element of S. Okay, well then maybe we'll include 3, right? And then 4 will not be included because 1 plus 3 is 4. And I think we can already see a pattern here, right? We just include all the odd numbers. If we try to maximize space in this manner, right, we get all the odd numbers, which actually makes sense because if we try to sum two odd numbers, we'll always get an even number. And since there are no even numbers here, there are only odd numbers, we can never get a form of a plus b equals c, because that would imply that an odd number plus an odd number is an odd number, which is never true. So this is actually a very efficient way of picking a subset, right? By picking all the odd numbers. But the question is that the most efficient way, right? So there are 13 numbers here. So we know the answer is not 12, but there's 3 more numbers here. How do we know that there isn't some way to change around some of the numbers to give 14? Well, the answer is that we should designate one number to be in the set and then focus all the other numbers in the set around it because of the sum rule. Basically, this rule is very powerful. So we can think, what number can we pick? We could start from the lowest or from the highest. If we start from the lowest, things actually get quite complicated. But if we start from the highest, things work out quite nicely. So let's say that 25 is in the set. Okay, let's say 25 is in the set. Well, then we could come up with pairs of numbers like the following, 1 and 24. Now, the reason why I call this a pair is because we can't have both of them, right? Because remember, we're saying 25 is in the set. 25 is in the set, but that means we can't have both of these numbers, because if we had both, then there would be a contradiction. 1 plus 24 is 25. Same thing for the numbers 2 and 23, and 3 and 22. And this continues until 12 and 13. And now we've just shown that here is one number, and then here's the second number, third number, fourth number. This is the 13th number. And we can't have more than 13 numbers, because if we did, then we'd have to have at least one of the pairs of numbers that would cause a contradiction. Okay, but what if 25 isn't a part of the optimal solution, right? So let's not look at 25. Let's say 24 is the highest number, right? So 24 is in the set, 25 is not. Okay, but then we can just pair it up like this, 1 and 23, 2 and 22, 3 and 21, and this goes down until we reach 12. And actually already, this is only 13 numbers, but we can go one step further and actually show that we only actually have 12 numbers in the set at maximum, because including 12 would lead to a contradiction immediately, because 12 plus 12 is just 24, right? So actually, here we only get 12, right? And we can continue this all the way down, and we can pretty easily see, like, if 23 is the highest number in the set, then we just use pairs 1, 22, 2, 21, 3, 20, and we would eventually end up at 11, 12. And this is already only 12 numbers. And we can see a pattern here where basically, if we continue, if the highest number in the set is n, right, then we can show that there's at maximum floor of n over 2, right? Which basically means that the highest number is when 25 is in the set, which gives us the floor, the ceiling, my bad. No, it's the floor of n over 2 plus 1? No, okay, wait. Okay, it is actually the ceiling of n over 2, right? So it's the ceiling of n over 2, and if we apply that to 25, we get the ceiling of 25 over 2, which gives us 13. Okay, this is number 15 of the AMC 10B. Let S of n be the sum of the first n terms of an arithmetic sequence that has a common difference of 2. The quotient S3n over Sn does not depend on n. What is S20? Okay, so basically we have some terms of an arithmetic sequence. Let's call the first term A. Then it just goes A plus 2, A plus 4, and so on, right? And the quotient S3n over Sn should not depend on n. Okay, Well, what is the nth term in the sequence? Well, it's just a plus 2 times n minus 1. That's the nth term. Okay, so then what is the sum of all of these terms? Well, by the formula for the sum of terms in an arithmetic sequence, we just get 2a plus 2 times n minus 1 over 2, right? The sum of the first and the last terms over 2 times the number of terms, which is n, right? So that's going to be in the denominator of our fraction. And in the numerator of our fraction, well, the thing is actually, if we go up to number 3n, it's a plus 2 times 3n minus 1. That is the 3nth term. And the sum of these elements would be the sum of the first and last over 2 times the number of elements, which is 3n. So we can cancel out these n's. We can cancel out these divided by 2's. We can cancel out these 2's. This is in parentheses, though. And what we basically get is that 3a plus 9n minus 3 over a plus n minus 1. This should not depend on the value of n. Okay, but the thing is, the only way for this to happen is basically if we can get the n's to cancel, right? We want this to not depend on the value of n. So the thing is, the way we could get the n's to cancel is by making these two equal to 0, right? We can both make them equal to 0 by making a equal to 1. And if we make a equal to 1, then it makes this ratio here, it makes that ratio just 9n over n, which is just 9. So a equals 1 is the term that cancels out the n's. So basically a equals 1. So 1, 3, 5 up to 2n minus 1. Right? That would be the nth term. So it's asking for s of 20. It's not asking for the 20th term, it's asking for the sum of the first 20 terms. We know that the 20th term is 39. So the sum of these terms would just be, well, once again, we use that formula, 1 plus 39 over 2 times the number of terms, which is just 20. And that gives us 400.